So today I have the pleasure of telling you something about PDEs that's extremely fundamental. Maybe the most fundamental things that you should know about PDEs and what their solutions look like. It is what I'll show you today, based on the technique of separation of variables, is totally classical and something that every applied scientist should know. And another nice thing is that the parallel to linear algebra is also very, very strong. So we'll first start with a slightly more general discussion. We'll talk about our now familiar heat equation in 2 dimensions. But then solving anything in 2 dimensions is by definition very, very difficult because we have a complicated domain. So we'll actually start solving these equations that we'll obtain in 1 dimension, on a straight line, on a segment. But the framework is more easily seen in this more general setting. We already know how the solutions to this equation behave, because this, being the heat equation, models relaxation to equilibrium. And I think I already used the word exponential relaxation, and we'll see that it actually is literally, there's something exponent, not something. It's very exponential. So this is exponential decay to the equilibrium. So what we imagine is this might be our 2-dimensional room, and there was a fire burning in the middle of the floor, and so it was hot in the middle, cold at the walls, and then the fire was extinguished, and now the room slowly equilibrates. What I'm trying to do right now is motivate why we would expect reasonably solutions to look like what I'm about to write down. But what you can sort of imagine in a way, and then it kind of works, but much more rich, in a more rich way, is that you have a certain shape, the initial profile, your initial condition, and then it slowly relaxes to the equilibrium. So it kind of keeps its shape, but the amplitude, if you want to call it that, decays. So what we're going to look for is a solution that looks just like that, a profile whose amplitude, let's say, depends on time. So it sort of keeps its shape, but its amplitude depends on time. So a solution like that will look like some function of x and y. Doesn't have to be x and y, it's better to say of space, because the equations that I'm about to write down will not assume that we use Cartesian coordinates or anything like that. One of the more interesting cases will be on the circle in polar coordinates. So it's better to say a function of space, without imposing coordinates on the space, times a function of time. And when we plug in that guess into this equation, something very nice will happen. We'll have a chance to separate our variables. Therefore, separation of variables. So it makes sense as an attempt? And then once this attempt succeeds, well, that'll be an opportunity to use the linear property of this equation. Because if I get a pattern for things that work, I can then add them together in any proportions, in any linear combination, and I will continue to have a function that satisfies this differential condition. And then the name of the game, the name of the remaining game, will be matching the initial and boundary conditions, which is far more difficult, because that depends on the geometry, on the whimsical conditions, on a whole slew of other things. So that's actually the hard part, and maybe a little bit less classical. But what sorts of things satisfy this differential equation? That's the classical part. So here's our guess. We'll represent this function of u, ooh. We want it in 2 dimensions. Great start, Pavel. Or better yet, I will write Laplacian. So the reason why I prefer this notation over this notation is because this notation doesn't tell you what coordinates you're using. I'm a big enemy of using a specific coordinate system too early on. So this says whatever, we have our invariant interpretation of the Laplacian. It's the degree by which the value at a point varies relative to the average of its, is discrepancy between the value at a point and the average of its neighbors. Nice invariant interpretation. You don't need specific coordinates. I know that's not what this course is about, but your minds are so corrupted by your addiction to Cartesian coordinates that I take every opportunity to highlight where it's absolutely not necessary. And for this discussion, it's not necessary. This could be in any coordinates or no coordinates at all. That's the benefit of this notation. And then there's an in-between technique. Once again, I should resist, but I can't resist, which says let's choose a coordinate system but not specify which one. So maybe get the benefits, most of the benefits of using a coordinate system, because who can deny that it's beneficial, but not specify whether it's Cartesian or polar or anything else. And that's called tensor calculus. It's the art of taking full advantage of coordinates without ever specifying what coordinate system you're working with. It's the golden compromise. Okay, so we're back here. We're looking for a solution. This is a function of t and the spatial variables. I'll denote them collectively by s, because I don't want to write x and y or r and theta. It'll be a product of a function of t and a function of the spatial variables. So here's what it will look like. U as a function of t and the spatial variables. So I actually prefer the letter z, if you would bear with me, because it's not x or y, it's z. And this capital Z, should I make it a lowercase z? Yeah, okay, capital. That's all right, that's fine. Capital Z will be a function, will be a product of a function that's a function of spatial variables only. That's sort of your shape function. I will actually call it f. And it'll be a function of your spatial coordinates, whether, once again, it's x, y, and z, or r, theta, and phi, whatever. Times a function that's a function of time only. And this is the sort of function that kind of has this shape. The only thing that changes is amplitude according to this formula. And I can now plug this into this partial differential equation. And you will notice that on the left, I only have a time derivative. So by the product rule, it will only affect this function. And it will be an ordinary derivative. It won't be a partial derivative anymore. And the Laplacian is only has to do with spatial derivatives, so this will come out as a constant, and we'll end up with the Laplacian applied to this function. So very nice. The time derivative goes on the time dependence, and the spatial derivatives go on the space dependence. Makes perfect sense. So let's plug it in, and notice that I will just use the notation t prime, because now it's an ordinary derivative. And so a partial differential equation will have some ordinary derivatives in it, maybe making it simpler. Much simpler, in fact. So here we go. Here's how the technique goes. When I plug this form into the time derivative, this remains unchanged, and we just have an ordinary derivative of this. So we'll have, and I'm dropping, I just want to focus on the bare essentials. So I'm dropping the independent variables. When you see f, you know it's a function of space. When you see capital T, you know it's a function of time only. So I will just write f t prime. That's the left-hand side. Ordinary derivative of t, the derivative that you learned in Calculus 101. Equals alpha, let's call this thermal conductivity. That's a good thing to call it. This equation is saying the rate of going to the equilibrium is proportional to the conductivity constant and also proportional to the Laplacian, so it makes sense. The higher it is, the higher this number is, the faster you'll get to the equilibrium. So alpha stays here. And then we end up with the Laplacian of f. Laplacian of f times t. Again, if you're a little bit uncomfortable with the symbol of the Laplacian, think of it as the sum of second derivative with respect to x and with respect to y. You can think of it that way. Just relabel it back to the Laplacian. Okay? With respect to, if you want x and y, then you're saying that you're using a Cartesian coordinate system. Okay? And then you do this standard step. You divide both sides by ft. And you will see that has the effect of separating variables. Everything that depends on time will stay on the left. Everything that depends on space will be on the right. And they won't mix. And that's the critical step in the argument. So on the left-hand side, we'll have T transpose. He's thinking MATLAB all of a sudden. The derivative of T, the ordinary derivative of T, that's the best advertisement for MATLAB. Divided by T, are you guys with me? When I divide this by Ft, F cancels and you have T prime divided by T. And this is a function of time only. That's how the argument goes. I buy into it, happen to buy into it, equals alpha times the Laplacian of F divided by F. And that's true. This has got to hold at all times, at all points in space. So no way could this depend on x and y. Because if this ratio depends on x and y, then how could the left-hand side keep up? You would go to a different point in space. This value will become different. Well, how could this value catch up if it doesn't depend on x and y? And this cannot possibly depend on t. Because if you keep the point but change the moment of time, well, if this does depend on time, then it would be a different value. But this side would be the same value. So if there's hope of finding a solution in this form, then both of these must be constants. This must be a constant, literally, not just constant with respect to one variable, but not others, just a number. This will be a number, and this will be a number. Now, let's play a little bit of a guessing game and guess whether that number is positive or negative. And as a physicist, there is no hesitation. As a mathematician, you're interested in what these equations do regardless of their physical interpretation. And if you follow that path, you will learn that if we chose that this would be a positive constant, you would run into trouble. It's possible, but there would be problems. So we know that it's a negative, it has to be a negative constant because we know what these equations are meant to describe. Relaxation to equilibrium. We want decays, exponential decays. We want things going down. So we want this derivative to be negative. We want negative exponentials. So we're expecting that this will be a negative constant. And how do we denote negative constants? Leave some space first. Well, you just pick a number and you say squared. A good letter to use is omega. So you say it's negative omega squared. And just for convenience, because we're just naming things, I will put alpha here. So in other words, I will choose my omega so that this constant equals minus alpha omega. That's just how I want, maybe from the point of view of units, physical units, from whatever point of view, that's how I want it. So it's basically redefining omega compared to having just omega squared here. Okay, so now we have two equations. It's important that not only is this a constant and this is a constant, they're one and the same constant. So we have two equations. This equals this, and this equals this. And what will be nice about it is that you will see the kinds of equations that you've never seen before. Not in ODEs, not in PDEs, yes, in linear algebra. So here's what you will see. Well, first, let's skip a step and do it in our minds. T prime over T equals minus this. Okay, so that means that T prime equals this number times T. And for the spatial equation, we have alpha will cancel, and we'll have Laplacian of f equals minus omega squared f. Laplacian of f equals minus omega squared f. Okay, let's knock off this equation, which is much more boring. It is an ordinary differential equation. Is it linear? Of course. Does it have constant coefficients? Of course. Do we know its solution? Of course. It's a decaying exponential. There's one kink here only. Something that we haven't encountered in ODEs, and that is we don't know what alpha or omega, well, we know alpha, excuse me. We don't know what omega squared equals. So there's an unknown. So where will it come from? So that's interesting. So keep that in mind. Does this correspond to our intuition? Yes, in every which way. Number one, it's an exponential decay. Exactly what we were looking for, giving validity to the term exponential decay. And also, the greater alpha, the faster the decay. Another nice feature. And interestingly, the greater omega, the faster the decay. That's, what will that mean? Well, it depends what's omega. That's the big question. Where will the value of omega come from? Question or answer? No. No, I want to milk it. Yes. Are you going to tell me it's going to come from the other equation? Yes, it will come from the other equation, but how? Oh yeah, I'll cut this out. Yes, you're not. Okay, now that we've knocked off this equation, let's talk about this one. Have we discussed this kind of equation before? Is it Laplace's equation? Definitely not. Laplace's equation is Laplacian equals 0. Is it Poisson's equation? No, because Poisson's equation is Laplacian equals something given. It's neither. It's a new kind of equation. Is it similar to some other equation you've seen before? What equation is that? Yes. Yes, it's exactly the eigenvalue equation, if you just say it in the right words. If you say Laplacian of f equals minus omega squared f, then it doesn't sound like the eigenvalue equation. But if you say a linear operator applied to f equals a constant times f, then it very much sounds like an eigenvalue equation. And let me just write it down. That's the most important part. This looks like ax equals lambda x. The second pillar of linear algebra. Yes? Yes, that's the most important question. Is the Laplacian linear? This would be mostly meaningless if the Laplacian wasn't linear. But Laplacian is linear. We actually discussed it in the last lecture, but that is a very important question. Whenever I write something down like this, I do a double take. Like, wait a second. Is it linear? Is my most important underlying assumption true? And yes, it is. Because it's the sum, in Cartesian coordinates, it's the sum of second derivatives. And each one of them is linear, so the sum is linear. Think about the invariant interpretation. It is the degree by which the value at the point exceeds the average of its neighbors. Does that sound linear? If you had two functions with two individual measures like that, and you added the functions together, and you ask the same question of the sum, would it be the sum of the measures? Yes, it would. I'm answering it very quickly. It takes a slightly longer pause. But yes, it's a critical question. Is it linear? And yes, it is. And let's remember something about this equation, which was a little bit funny, because let's say we're in n dimensions. When we're in n dimensions, the thing that was a little bit unnerving at first is that there are n plus 1 variables, because you want to know your x, and that's n unknowns, plus lambda is unknown. I'm trying to stress this. It's not an equation that we've seen before, because we don't know what omega is. Omega needs to come from the problem itself. So we'll see how it happens. It happens in a very nice way, yes. No, because The fact that it's second derivatives, and that's where you want the square, is a detail here, secondary to the fact that it's a linear operator. Even if it was Laplacian of the Laplacian of the Laplacian, actually Laplacian of the Laplacian has a name, I forget what it's called. Even if that was the case, I would still write A, because the essential part is that it's a linear operator. Now, I might write minus here to match this minus, which doesn't change anything, and it's often done for reasons that will become very apparent very soon. We'll discover that all of the eigenvalues of the Laplacian are negative, making it something very important that we'll discuss in today's Linear Algebra 2 lecture, actually. Quite interesting how the two classes overlap now. Okay, so we have n plus 1 variables and n unknowns. But things worked out just right. We were able to first determine our eigenvalues through the eigenvalue equation or whatever, polynomial, characteristic polynomial, and solving it or in some other way. And then given that, we could kind of determine x. But of course, not precisely, but up to a constant, up to its being part of the eigenspace. And that's how this n plus 1 unknowns versus n equations worked out. You can't nail down the variable. You can only nail them as a set up to a constant. That's if the eigenspace is one-dimensional. So we can hope that the same sort of thing will happen here. That when we look at this equation on this domain, and now there is no time left, it's only spatial variables, that somehow the eigenvalues, the omegas, will be determined. And that's the most interesting thing. So of course, I don't actually know what this is called. I call it the Laplace eigenvalue equation. Does that make sense? Because there's a Laplace operator, and it's an eigenvalue equation. So I like to call it the Laplace eigenvalue equation. The omega squareds are called the Laplace eigenvalues. What do the Laplace eigenvalues, what are they descriptive of? Of course, they're descriptive of this domain. It will be this domain that dictates the Laplace eigenvalues. Not only the domain, very importantly, but the boundary conditions. And you will learn in just a second, because we'll kind of repeat the same discussion, but for the wave equation. We will end up with something slightly different in space, in time, and an identical equation in space. And then we will learn that these eigenvalues correspond to the frequencies that we hear. So you can call them pitches, to the frequencies that we hear. And we know from intuition that the boundary conditions matter very much. For example, if you think of it as a drum, and this drum is intact all around, the boundary condition that would correspond to is that F on the boundary equals 0. But suppose this was a strange drum where along here it's fixed, but along here it's just loose in the air. For example, the stitching ripped and it's just loose. When you hit the drum, it will sound totally different. Not just in terms of the quality of the tone, but the pitch will change. So what the pitch depends on is not only shape, but what happens on the boundary. So that's what we'll discover once we get into this equation. But before we do, I want to repeat this separation of variables logic for the wave equation. And we'll go through it relatively quickly, because we'll get something very similar. Except, what do we expect that's very, very different? Well, of course, we're not going to get exponential decay, because the wave equation is about rushing towards the equilibrium and then overshooting and then rushing back. So that's what we're going to see. All right, wave equation. We kind of know where this is going. So we're going to we want a positive number here. So I'm now calling it c squared. Of course, we want alpha to be positive as well. But now it will actually pay to have a positive number here. Okay? So we'll look for the same sort of thing. We'll look for time to separate from space. When we separate time and space, we think of u as a function of time only and as a function of space, dropping all the variables. You can see how the variables work right here. Well, I did it in the opposite order, but the product is commutative, isn't it? How nice. They're not matrices. Okay, plugging it in, we get now the second derivative of the capital function t, of the function capital T, times u equals c squared. T is unchanged, and f ends up under the Laplacian. And now we'll divide both sides by tf, canceling this f and canceling this t. Okay, exactly what we want. Nothing but time on the left, nothing but space on the right. So they must be constants. Once again, we'll conclude that it has to be, does it have to be a negative constant this time? Gee, I don't know. Yes, it does. Yes, it does. Yes, it does. So we're going to denote it by negative. Once again, we'll throw c squared into the mix because it's convenient. Omega squared. I think we'll see why we want. So do you see how it wasn't at this point, I had no basis for choosing a negative constant. But when I got to this point and I said, I want exponential decay, then that's when you realize that you should have chosen a negative constant. So of course, preparing for this lecture, as I was walking over here, I kind of thought to myself, do I want a positive constant or a negative? So I took it a step further. And at this point, I realized, oh, I want a negative constant. So I went back and, that's how it works. It's when you get to the solution, when you get further on, you realize the decision you should have made. And as mathematicians, you should go back and wonder, well, what would happen if I put in a positive constant? Mathematically, it's 100% valid. So you should just develop that idea further until you hit a snag or realize that it's not possible for whatever reason. Or maybe it's just inconvenient, right? It's just, right now we're just putting a minus sign in front of it, really. That's all we're doing. Especially when you have complex numbers at your disposal. You can let the algebra decide for you later what it should be. Okay, so we'll once again say, well, we already did say it. Both are constants, so we have this ODE. Okay, and on the right, well, it's the exact same eigenvalue equation. I should write it down for completeness. Okay, so this part of the equation is exactly the same, the Laplace eigenvalue equation. I think it deserves attention. What do we have here? Familiar equation? Sines and cosines. So t, I'll just write it down. It will be a linear combination of sine c omega t and cosine c omega t. Okay, so the next thing I'll tell you, well, it's obvious what happens, what the next step is before you get to concentrate on this equation. You have to acknowledge the fact that these equations are linear, both heat and wave equation are linear. And so if we found what sort of thing satisfies the equation, we can put them into any combinations that satisfy the equation. So let's do that now.